Okay, guys, we're going to go ahead and get started. I still got a few. Okay, I think. All right. So I have a paragraph on the board. If you have pen or paper, if you want to get pen or paper, you'll need your coloring pencils. You'll need something to take notes on. I want to talk about a couple things today, and then we do still have an exam. Is my audio okay? Can everybody hear? Okay.
You're
All
coming
right.
in good.
All right. Is that
I can hear
sound?
you too.
All right. Beautiful. All right, great. Now I know we tried to do a test run over the weekend. There was a little bit of glare on the board, so hopefully you can still see. I want to try to find a room that's better, has better lighting to get rid of that glare, and I can use more of the board. But go ahead if you don't. I'll give you a minute to get your pen, papers. You want to copy this down. I'm going to put a document for this on Blackboard, so you'll have this. But go ahead and copy this down now. I'll give you a second to do that. And I want to talk about this now. I mentioned in class that we need to have an exam two, which will cover series. It'll cover parallel. It'll cover. We did empire rating. I'll put a list on the board. I still plan to do that. The topic we're going to cover today, actually, there's two topics, will be part of that exam. And once we finish covering this topic, technically you're ready for the exam. I just got to figure out, since we're doing this thing by remote, how to deliver it. So the point is, don't worry about the exam right now, but do get this in your notes, and you want to make sure you understand what I'm doing. So I'll give you a second to copy this down because I want to erase it. So copy this down, and then I'll start. The other thing you want to keep doing, what we're going to do today, you need to be kind of at least working on the series parallel stuff. So I know we just did this, I guess last Wednesday I gave you a sheet. We did a few practice problems on series parallel, and you need more practice with that. I'll post some more problems with solutions up on Blackboard in the next couple of days. So I want you to keep practicing the series parallel, but you need to practice the stuff we're going to do today also. And if you can do this, you can do series parallel and vice versa. So let me go ahead and start. So I want to talk about two things today. I want to talk about a theorem called Thevenin's theorem. To me, second to Ohm's law. This is probably the most important thing. Second to Ohm's law. So it's very important. Has a lot of applications. And if you take AC, especially if you take me for AC, I will come right back to this. So this actually it answers a lot of questions too if you understand the theorem. So just for me to read this, I'll read it, and it's a lot of words here, but the actual theorem is pretty simple when I show you the diagram. So this is called Thevenin's theorem. Thevenin's theorem. And Thevenin's theorem states that any two-terminal linear bilateral DC network can be replaced by an equivalent circuit consisting of a voltage source and a series resistor. So it's a lot of words, but what does it mean? So basically what Thevenin is saying is that this idea of equivalent circuit, I think we kind of know what an equivalent circuit is, but so far we've been looking at circuits from the point of view of the voltage source or battery. And I want to show you what I'm saying, what I mean. So if you got this down, I'm going to erase the board. I'll give you another second in case you got to copy it down real fast. But I want to show you what I mean by point of view of the battery. We'll give you a really simple circuit. All right. Give me a second. I got a mic cord here. I don't want to trip over it. Have you guys laugh at me? Let me get this together. Okay. So now notice how this circuit is drawn. So why did I draw it like this, and what is this? So typically we've been talking about these circuits with resistors. We'll talk about some other devices like capacitors, inductors, what have you. But usually you deal with devices, you deal with things like a cell phone or a TV set. You deal with some kind of electrical device. And any device is going to have at least one input and one output. For example, I might have an amplifier, maybe an audio amplifier. I guess you guys can see this. So I have an amplifier that you would hook up in your car, and that amplifier will be connected to a speaker. So that might be your speaker. And this end right here, you might hook your radio. So this is a car amp. Well, where I put the energy or power into, that's the input. Where I get the energy or power out of, that's the output. So typically we draw a circuit, but what I'm trying to indicate here by putting these little circles there, that's like a terminal. You would connect up, say if this was an amplifier, maybe this would be your speaker. Or this were your cell phone charger, maybe this would be your cell phone. So this represents something that you would connect up to a circuit. And this L here next to the R represents a load. So when you connect up something to an electrical device, your cell phone charger would be a good example. You got your charger and you connect your cell phone to the charger. Well, that cell phone is then considered what we call the load. Or in this case, if I have the amplifier, that's a circuit. The thing I hook to the amplifier, I call that the load. So what I'm trying to indicate here is I have a circuit. And connected to that circuit, I got this resistor I'm going to identify as the load. So I draw these circles there to represent terminals that I will make some kind of connection to. Now, I want to talk about the resistance of, let me put a box around this. So this is the device. So that's the circuit of interest or the device. I want to talk about the resistance of what I have in that box, not the load. So what I'm saying is, let's say we're talking about your cell phone charger. Your cell phone charger and the cell phone are two different devices. You hook your cell phone to the charger. So the cell phone is the load. So if I ask for the resistance of the cell phone charger, you wouldn't give me the resistance of the cell phone charger and the cell phone. In other words, the load is not part of the circuit. So I'm trying to indicate that with this box, this indicates the circuit or the part of the circuit that I'm interested in. So if I want to know the resistance of the device, of the circuit, I wouldn't keep this connected up to it. If I want to know the resistance of your cell phone charger, I wouldn't have my cell phone connected to it. So what I'm going to do here is I'm going to remove the load. I'm removing the load because I'm only interested in the properties of the actual thing that I'm talking about, the actual circuit. Now, let me put some values here. Let's make, I don't know, let's make this, we'll make this 6 ohms. We'll make this 3 ohms. We'll make this 9 volts. If I gave you this circuit and I told you to find the total resistance of the circuit, what would you figure out? What would the total resistance be? What's the total resistance of the circuit? And Sam said, oh, I'm sorry. Sam? Can you talk, Sam? Can you hear me?
Yeah, I can talk. It's in series with each other, so you would just add 3 and 6 together to get 9, right?
Exactly right. Now I'm just curious, can you guys hear Sam? Can you guys hear each other, or can you only hear me?
Yeah, I can hear Sam.
Okay,
I can
all
hear
right,
everybody.
so this is actually kind of cool then. So Sam is exactly right. this is a series circuit, and the way Sam said you would get the total resistance is by adding the 3 and the 6 together. But kind of what you did without knowing it, you gave me the resistance from the point of view of the battery. In other words, you gave me the resistance looking this way. And that's how I taught you all semester to do it. Anytime we did the calculation, we always did it from the point of view of the voltage source or the power source. This thing I'm going to talk about today, Thevenin's theorem, there's two ends to the circuit. There's the point of view of the battery, but then there's also the point of view of this thing right here that I'm calling the load. There's actually two resistances here. If I ask for the resistance from the point of view of the battery, we'll call that the input resistance. If I ask for the resistance from the point of view of the load, that means instead of looking this way, I'm looking this way, and that's called the output resistance. So anytime you have some kind of a device or circuit that makes up a device, you'll have an input and you'll have an output. Therefore, you'll have an input resistance and you'll have an output resistance. You'll have input voltage, you'll have output voltage. And all semester, we've only been looking at circuits from the point of view of the voltage source. So if I ask for the input resistance, we call that also the total resistance. We call it the equivalent resistance if they were parallel. But all of this is the resistance from the point of view of the voltage source. Well, what Thevenin says is there actually is a resistance from the point of view of the load that might be different from the resistance from the point of view of the voltage source. So the voltage source, as Sam said, the voltage source sees a resistance of 3 in series with 6. It sees a total resistance of 9. What would this thing over here say? What would this battery say? Or what would this resistor say? Well, to answer that question, we got a little problem we have to overcome. The problem is, if I hook up my ohm meter to this point right here to measure the resistance, I really wouldn't get a correct value because I got this voltage source there. You can't measure the resistance of a circuit with power hooked up to it. So how would you get that resistance? The answer is what you have to do is you have to take the power source and set it to 0. So make sure you have a notebook. I want you to write something down for me. You already wrote down Thevenin's theorem. What I'm going to do is go through some steps that I'll give you to apply that theorem. But one thing you're going to write down, one thing you have to understand is how do I set a power source to 0? Well, so far we've only talked about one kind of power source. That's a battery, a voltage source. You may have read about, in I think chapter 2, there's another kind of power source called a current source. One of your homework problems referenced a current source. So there's two kinds of power sources. 99 times out of 100, you will only deal with voltage sources. But in some places in electronics, you'll deal with current sources. So I want you to write something down. If you want to set a voltage source to 0, you replace it with the short circuit. And I'll say that a second time. If you want to set a voltage source to 0, you replace it with the short circuit. There's another kind of power source called a current source. If you want to set a current source to 0, you replace it with an open circuit. So if I have a voltage source, I'm going to replace it with the short circuit. If I have a current source, I replace it with the open circuit. Now let's talk about what that means. What does it mean to set it to 0? Well, what it means is, let's say I have a battery. I have this battery. I'll just make it a 10-volt battery. If I make it 10 volts, and let's say you have your voltmeter hooked to this. So you got a voltmeter hooked to it from there to there. If you hook a voltmeter across a 10-volt battery, of course it's going to read 10 volts. While that's hooked up, let's say you take a wire and you connect the wire from here to here. Now you can't do that in real life. Bad things will happen, so don't try this at home. But if you were to do that, connect the wire from the positive terminal to the negative terminal, the battery would probably end up blowing up. But other than that, what you would notice is this voltage would go to 0 because this wire represents a short circuit. So a short circuit, an ideal short circuit can be represented by just a wire with zero resistance. So if I want to replace this with the short circuit, I would erase this and just draw the wire in there. There's another kind of a power source called a current source. I'm not going to say a whole lot about it, but you may have seen this in your book. It looks like this. That's a current source, and they usually show a resistor in parallel with it. But if you had this in the circuit, to set that to zero, you would replace it with the open circuit. In other words, you would just remove it from the circuit. But for right now, we're going to work with voltage sources. So let me back up and make sure I'm clear on that you understand what I'm saying. So what I have is I have this circuit, and I had a part of the circuit that I call the load, which is something hooked to the circuit. The load is not part of the circuit. It's something external to the circuit. I gave an example of this might be your cell phone charger. This might be your cell phone. Your cell phone is a separate thing than the charger. So if I ask for the resistance of the cell phone charger, you would have to disconnect the cell phone. You would have to disconnect the load. So this idea of this Thevenin circuit idea, what I do is identify one of the resistors as the load. That's the resistor of interest. And then the rest of the circuit, I can look at from the point of view of the voltage source or from the point of view of the thing that you identified as the load. And then the thing to remember is that looking one way in the circuit, I see a certain set of parameters. I'll see a certain resistance, a certain voltage. I'll see something different from the point of view of the load. And I want to demonstrate that to you here in just a second. Well, we've already said if I ask the total resistance of the circuit, then Sam correctly said, well, that's easy. Just add them up. They're in series. So the total resistance, he said, was 9 ohms, and that's correct. But what is the total resistance from the point of view of the load? If I want the total resistance from the point of view of the load, if I try to put my ohm meter here, I wouldn't get a reading because that power source is there. So what I have to do is I have to set the power source to 0. And the way you do that is by removing it from the circuit and replace it with the short. Now when I hook up my ohm meter, I will get a reading. But the question is, what value would I get? Well, when I asked about the total resistance, and Sam said it was 9, that was the resistance from the point of view of the voltage source. And Sam correctly said that, well, you got a series circuit. These two resistors are in series. Looking this way, you have a series circuit. But looking this way, what kind of circuit do you have? Well, it's not series because if you think about it, if you sent current in this way into the circuit, the current will split off and some of it would go that way and some of it would go that way. So from the point of view of the load, looking in the circuit this way, what you actually have are two resistors in parallel. Looking this way, the two resistors are in series. Looking this way, the two resistors are in parallel. So looking from the point of view of the voltage source, the resistance was 9 ohms. But from the point of view of this resistor here, we call it the load, that total resistance would be 3 in parallel with 6, which turns out to be 2 ohms. This resistance is called the output resistance, or out. Well, in practice, it's called the output resistance. In your textbook, they'll give it another name. They'll call it the Thevenin resistance. The Thevenin resistance. And they usually denote it like this. So what you need to write down is the Thevenin resistance is the resistance from the point of view of the load. The total resistance is the resistance from the point of view of the voltage source. The total resistance or the input resistance. So I don't know if that was confusing or not, but I think it'll be clear. Let me erase this. I'm going to redraw it. So what I need for you guys to do is get ready because I'm going to give you a list of things to write down. I'm not going to write it on the board, I'm just going to say it. So I'm going to start with the same circuit I just erased. Okay, so you want to start your notes here and draw this circuit. I'm going to give you a set of steps to write down. What Thevenin says is you can have any circuit as long as it's a linear bilateral DC network. You don't have to really worry about what those words mean right now. But what he says is you can take virtually any circuit and reduce it down to this. You can take any circuit, no matter how many resistors, no matter how many voltage sources are in that circuit, and you can reduce it down to a simple series circuit that consists of a single voltage source and a single resistor. And if you notice, I labeled this VTH. That's called the Thevenin voltage. And I labeled this RTH. That's called the Thevenin resistance, or the output resistance of the circuit. So Thevenin says that you can take any circuit, virtually any circuit, no matter how complicated, and you can reduce it down to this. And this is called the Thevenin equivalent circuit. And this circuit is equivalent to the original circuit from the point of view of the load. That's the important part. So what we need to be able to do is to go from this to this and get the proper values of VTH and the proper value for RTH. So what I want to do is give you a list of steps to properly, we say, Thevenizing a circuit. I'm using it as a verb now. To Thevenize means to go from this to this. So get your pencils, papers ready, and I'm going to give you a list of steps to go through, and then we'll actually do it on this circuit, and then we'll practice with another problem or two to make sure you have it. So what I want you to write down is this. These are the steps. These are the steps to properly Thevenizing a circuit. So write that down. The steps to properly Thevenizing a circuit. And by the way, this should be in your book. It may not be in this order, but it should be in your book. Okay, so step one. And if you don't get it, you don't get the steps, I'll say it, and then I'll go back through it when I actually do it. So if you miss a step, it's okay. We'll repeat it. So step one, the steps to properly Thevenizing the circuit. Step one, you want to remove the load. Remove the load. Step one, remove the load. Step two, you want to name or mark the terminals. Name or mark the terminals, and I'll give you the reason for that in just a second. So step one, remove the load. Step two, name or mark the terminals. Step three, you want to find the open terminal voltage. Let me write that down. Open terminal voltage. And all that means is these are the terminals. To open the terminals means you're going to remove the load. So we've already done that in step one. So you got to find the voltage at the terminals with nothing connected to it. So find the open terminal voltage. Whatever value you get for the open terminal voltage, that's your Thevenin voltage. I think I'm step 4. You're now going to set the power source to 0. So go ahead and write that down. Set power source to 0 for step 4, but there's an A and B there. So step 4 should be set power source to 0. And under that, put step A. So step 4 is set power source to 0. And A is, if you have a voltage source, replace it with a short circuit. If you have a voltage source, replace it with a short circuit. If you have a current source, replace it with an open circuit. A current source replaced with an open circuit. And then the final step, this gets you the value of RTH. Look into the output terminal and figure out the resistance from the point of view of the output terminal by looking into the output terminal. So I went through those steps kind of quickly, but I think it'll be easy when I actually show you how to do it. So here's what we're doing. We're doing 2 things. We got to find the value of VTH in this circuit. We got to find the value of RTH in this. So we're going to go through those steps again that I just gave you, but this time we're actually going to do it on this circuit. So step 1, the first thing I said we had to do, you got to remove the load. So on your, oh, I just lost my, can you guys still see? The lights went on. Can you see or not?
Yeah, I can see.
All right, because the motion detector, let me see if I can get the motion to come back on.
You're fine as is.
Okay, all right. All right, so step 1, we're going to remove the load. So you can't do this on your paper, so you have to redraw it. So I'm going to remove the load. Just erase it. But you go ahead and on your paper, you draw another circuit for each step that I'm giving you. The first step is the original circuit. The next thing you draw will be this circuit with the load removed. So the first step is to remove the load. Once you remove the load, you're going to mark or name the terminals. Now, all that means is name this. I usually call this like terminal A, and maybe this one terminal B. The reason you do that is, well, this is a really, really simple circuit, but the circuit can be really complex, and as you'll see in the future lecture, sometimes you got to redraw the circuit and things move around. And so you want to be able to keep track of these, and by naming them, it makes it easier to keep track of. So you're going to mark the terminals. I call this terminal A and this terminal B. So that should be a separate picture by itself in your notes. The next thing you want to do is to measure the open terminal voltage. And what that is I removed the load already, so these terminals are open. That's the meaning of open terminal. These terminals are open. Now, if you had a voltmeter and you put that voltmeter between these 2 terminals, what would it measure? And whatever the answer to that is the value for VTH over here. Well, how do you get that? Well, it actually is pretty simple, because once I remove the load, what I have over here is a series circuit. And so if I put my voltmeter here, really what I'm doing is measuring the voltage across the 6 ohm resistor. So the voltage between terminals A and B is just the voltage drop across R2. Hopefully you can see that. If I measure here with my voltmeter, all I'm doing is measuring across that resistor right there. So if you can find the value of this, then you got the value of VTH. So how do you get that? Well, that's pretty simple, because it's just a series circuit. So there's really 2 ways to do it. The way I taught you in class, and then there's something called the voltage divider rule, which I tend to use when I'm using these kind of problems. So let's do it both ways. So I want to find this voltage across R2. The first thing I would do when you solve any series circuit where you know all the values, the first thing you do is find the total resistance. Well, Sam already gave us that. He said the total resistance was 9. So I got 9 ohms for the total resistance. Then the next thing you would do is use that total resistance to find the total current. Well, that's easy because the current total is just my total voltage divided by my total resistance. So that means I have 1 amp flowing. So I have 1 amp flowing in this circuit around this loop. And then the last thing you do to find the voltage across that resistor is you just take, I'll call it V6, and you multiply current times resistance. And that'll give me 6 volts. So I have 6 volts from terminal A to terminal B because I got 6 volts across R2. So that's one way to get that voltage. That's the way I showed you in class. But there's another way to get this. I'm not sure if I talked about the voltage divider rule in class. I think I did, but I'm not certain. But if I didn't, I'll do it right now. It's pretty simple. And normally I would derive this, but since we're doing this remote thing, I don't want to get into too many derivations. I'll just give it to you. The voltage divider rule says if I have this resistor, I'm just going to call the resistor Rx. And you know, you name a voltage drop after a resistor, right? So if this was R2, then this voltage is V2. The voltage across this resistor, R1, and we call that V1. Well, if I have a resistor called Rx, the voltage across it, I would name that Vx. So if I want to know the voltage across a resistor in a circuit, in a series circuit, what I can do is take the resistor, divide by the total resistance, and then multiply that fraction by the total voltage, and that'll give me the voltage across the resistor. It'll give it to me directly. When we did it this way, if you remember, we had to go through 3 steps. We had to find the total resistance, then we use that to find the current, and then we use that current to multiply by this resistance to get the voltage. So we had to find current. Basically doing it this way, we never have to do that second step of finding current. So I tend to use this rule right here when I'm doing these kind of problems. So if I do it as an example, I want to know the voltage across the 6 ohm resistor, so I'll put that in the numerator. I divide by my total resistance. Well, Sam told us the total resistance, we figured out was 9. Then I multiply that fraction by the voltage source, value of the voltage source. Well, that's 9 volts also. And then what happens, I got 9 upstairs and downstairs. So all I have left is 6, so it's 6 volts. So you'll see me do this in the future. So I don't want to confuse anybody as I'm using voltage divider rule, but you can do it any way you want. The point to remember is the voltage across this resistor is the voltage that I get right here between terminals A. So that becomes my Thevenin voltage. VTH for this circuit is 6 volts. Well, what does that mean to say the VTH is 6 volts? Well, we know the voltage from this way is 9 volts, but the load that I took off, it doesn't know anything about a 9-volt battery. It only sees 6 volts. The thing that I took off only sees 6 volts. 6 volts. It sees this right here. So we found our Thevenin voltage, 6 volts. Now we got to find RTH, the Thevenin resistance. So how do I find RTH? Well, the next step in your list you should have is what I'm doing is I got to find the resistance. No, the resistance looking this way was 9. I got to find the resistance looking in this way. So I'm going to draw my little arc. I'm looking in this terminal right there. Well, to do that, you have to set the power source to 0. How do you set the power source to 0? If it's a voltage source, I replace it with a short. If it's a current source, I replace it with the open circuit. So I got a voltage source, which 9 times out of 10, that's what I'll give you. So I erase this, and I replace that with the short. And I use just like this. A piece of wire is what that represents. Well, if you do that, hopefully you can see that if I connect right here with my ohm meter, these 2 resistors are now in parallel. again, as I said before, if current went this way, it will split, and some will go that way, some will go that way. They're not in series. If they were in series, they both have the same current. But the fact that the current was split means that these two are in parallel. If you can't see that, just take this resistor and move it right there, and you'll see you have a resistor there and a resistor there. They're in parallel. So to get the resistance from the point of view of the load, the Thevenin resistance, what I actually have is I have 3 ohms in parallel with 6 ohms. And if you do the math, you'll find out that that's 2 ohms. You can do product over sum. You get 2. I do 1 over R, you'll get the 2. The point is, this value right here is 2 ohms. So my Thevenin circuit looks like this. Well, what does this mean, that the Thevenin circuit looks like this? Well, what it means is, if I go back to the original circuit, put my voltage source back in here. And I connect my load up. I'm going to clean this up a little bit. Let's say I put my load back. Now notice I never gave the load a value. I never gave it a value. Because really, for what we're doing, it doesn't matter. So if I did that, the Thevenin circuit, the Thevenin equivalent circuit, and the original circuit are equivalent circuits from the point of view of the load. So what that means is, if I took the load off of this circuit and moved it over here, it couldn't tell which circuit it was hooked to. From the point of view of the load, this circuit and this circuit are exactly equivalent. This load, even though we see a 9-volt resistor here, a 9-volt voltage source, and we see a 3 ohm resistor and a 6 ohm resistor, what the load sees is it sees a 6-volt voltage source and it sees 2 ohms of resistance. The source sees something else. The source is 9 volts. It sees 9 ohms of resistance. That's the input resistance. So the Thevenin equivalent circuit gives you an equivalent circuit from the point of view of the load. And you don't know it right now, but that turns out to be extremely important. Extremely important. So what I want to do now is I want to put another circuit on the board. Hopefully you got the steps. I'm going to put another circuit on the board, and I want you to go through those steps and try to Thevenize it. I want you to give you a circuit like this. I want you to give me the Thevenized version of it by following those steps that I just gave you. But before we do that, there's one more thing. There's actually another theorem called maximum power transfer theorem. I'm going to write down what I said, maximum power transfer. Maximum power transfer. So write that down somewhere. So in my mind, the most important thing we'll ever talk about in this class is Ohm's law. Because without Ohm's law, you can't do anything. The second most important thing is this, I just showed you right here, Thevenin's theorem. Behind that, the third most important thing is going to be this maximum power transfer. And actually, it's a maximum power transfer theorem. And I could read it. There's a lot of technical words, but it's pretty simple. What it says is you'll get maximum power transferred from the source to the load when the source resistance and the Thevenin resistance are the same value. So in other words, if I look at this circuit, I'll get maximum power from the battery to the load when this resistance and this resistance match each other. So if I want maximum power transferred to this thing, then I would have to make this 2 ohms. Erase that. I would have to make this 2 ohms. Any other value, you wouldn't get maximum power transfer. here's a practical example of this. Some of you guys, I don't know, you may have, they say you hook up a amplifier in your car. If you're in the car audio, let's say you got an amplifier. I'm going to erase this. So let's say you have an amplifier. And if you ever hook up an amplifier, probably stamped on the output of it, either the left or right channel, they'll say, all right, I need usually 2 ohm speakers, 2 ohms. And so what you would do is you would take your output and you go get some speakers and you connect them up, and they're saying, well, those speakers need to be 2 ohms. Let's just say this is a 100-watt amplifier. What they're really saying is, looking into the output of this amplifier, the Thevenin resistance or output resistance is 2. And if you want maximum power, you want all your 100 watts to go from here to here, then this had better match the resistance of this thing looking into the output. So if the resistance of this is 2, and you want maximum power transfer, then you got to make that match. Now, you guys actually proved this without knowing it, because the other day you did a lab. Remember the power lab you did? I think the last lab you did was the power lab. In that power lab, you had a circuit where you had a resistor. I think it was 2.7 k ohms. And you had a potentiometer. And I forget the voltage. It might have been 15 volts. I don't know. Let's just say it was 15 volts. It doesn't really matter. So in the lab, you had this circuit, and they told you to connect up the potentiometer as a rheostat. So you did this. And you called this one right here R1. And you called this one R2. And what you did, you took voltages across R1, and you took voltages, you found V1 and V2 for a whole bunch of data points. And then they had you make a graph. And if you remember, when you made the graph, I signed off on your paper, but I told you, I need you to calculate the power for this resistor. I need you to calculate P2 before I can let you go. And I was looking for those numbers, and what the numbers did, if you made the graph, your graph on this axis was R2, on this axis was P2. And if you made the graph correctly, what you noticed was the graph started like right here, it went up, it kind of peaked, and then it kind of went over like that. I forget the experiment number, but I think it was the last lab you did. Well, the reason I wanted to look at your numbers was to see if you were getting this peak. What you were proving was this right here. What you should have noticed, and if you still have that lab, when you write about it, you want to write about what I'm telling you right now. You should notice that as you turn this potentiometer, the closer this value right here got to that value, the higher the power went. If you look at your data, right around when this got to be equal with that, that's when this peaked. When you went beyond that or less than that, you were on this side of the curve. You only peaked right here, where R1 was approximately equal to R2 is what you should have saw. And that's the reason I had you do that lab, because I was going to show for this theorem, you basically proved maximum power transfer theorem. So the point is, and this is very, very important in the area of communications, audio, this comes up a whole lot. I can't emphasize it enough. So maximum power transfer says if you want maximum power transfer from any kind of voltage source to a load, if that's your objective, maximum power transfer, then you got to make these two resistances equal. And what it says is for maximum power to happen, for this to be true, RL has got to equal RTH. So write this down for maximum power transfer. Now, it's 152. So what I want to do, I'm going to put a circuit on the board, and I'm going to give you some time to work on it. I'll put it on the board. I want you to Thevenize it. Give me this circuit. I want you to give me the value of RL for maximum power transfer. And then what I'll do is I'm gonna put this paper on Blackboard with some other problems for you to work. And we're gonna practice Thevenizing for a while. We'll do some today and we'll do some more next time we meet. So I'm going to erase the board now. I will give you an example problem for you to practice. So make sure you have your calculator and paper while I'm putting it up on the board. And then I'm going to move away from the camera because the lights went out. I'm going to turn the lights back on, and then we'll run through the practice problem. And then I'll put a couple more problems up for you that will work next time we meet, which will be Wednesday. And I'll tell you about lab too. I want to make sure you're clear on what we're going to do for lab this week. I'll tell you before we end the session today. So let me clean this up. And I'm going to give you a practice problem. I want you to go ahead and try to work it, and then we'll work it together. And then I'll tell you about the lab, and then we'll call it a day. We'll end it. And by the way, I don't think I mentioned this. I'm actually recording this session. So if you miss this or someone misses it, I'm either going to post it to I'll post it on Blackboard or YouTube or something. I'll let you know where that is. So you'll be able to play this back over and over again. So let me give you this circuit, and I want you to get a piece of paper, get your calculator, and I want you to Thevenize this circuit. All right, here it is. I got a 32-volt battery, got a 12-ohm resistor here, 4-ohm resistor here. Here's my load resistor. And what I want you to do is to turn that circuit into this one. So what you got to do is you got to find VTH. I want RTH. I want the value of RL for max power. So go ahead and see if you can figure that out. And while you guys are working on that, I'm going to walk away from the camera for a second and turn the lights back on, and I'll be right back. So go ahead and work on that. Okay, guys, I'm back here. All right, so we want to Thevenize this circuit. The first thing we're going to do is remove the load. I'll just do that. The next thing I'm going to do is mark the terminals. I'll call this one terminal A, and this is terminal B. Now over here, the equivalent circuit, and this would be A, and that would B. I didn't do that in the last problem, but you want to go ahead and do that. Mark this how you mark that one. All right, so I've removed the load. I've marked the terminals. Now I got to figure out the open terminal voltage. These are the terminals. So with it open, with RL disconnected, what voltage would I measure across this resistor? And what I would see, if I connect my voltmeter up from A to B, then that's like connecting up across R2. So connecting here is exactly like connecting there. So if I find the voltage drop across R2, I found the voltage out here. And whatever that value is what you write right here. So I'll give you a second. Go ahead and do that if you haven't already done it. You can use Ohm's law like we've been doing all semester. I'm going to use the voltage divider rule to find it that I showed you a second ago. So give you a second. And if I use the voltage divider rule, what I do is find VTH. My voltage divider rule, I take the resistor I want to know the voltage across and put that in the numerator. So I want to know the voltage across R2. I'll put that in the numerator, 4. Divide that by the total resistance. Well, the total resistance is always the resistance from the point of view of the battery. So total resistance, looking this way, it's a series circuit. So as Sam mentioned in the last circuit, it's a series circuit, so I just add these up. I got 12 and 4, 16 is my input resistance or my total resistance from the point of view of the battery is 16. So I take the resistor I want to know the voltage across, 4, divided by my total resistance, which is 16, multiply that fraction by my total voltage, 32, and that'll give me VTH. It's 32 volts. If I do the math, that's a 2. If I multiply that, what I get for VTH is 8 volts. So your calculation, what you should have gotten for VTH is 8 volts. The next thing you're going to do is treat the value for RTH. So I'm going to move this stuff out the way. And for RTH, when I find the resistance, what I have to do, I'm looking in this way, and I need to find the resistance looking in this way. The Thevenin resistance is always the resistance from the point of view of the load. So it's like hooking the ohm meter over here instead of on this side. Well, looking in that way, I cannot find the resistance until I set this to 0. It's a voltage source. The way I set a voltage source to 0 is I got to replace it with the short circuit. Well, notice that these two resistors are already connected right here. When I put that short circuit there, it's going to connect the other side of these two resistors together, and that makes them in parallel. So looking this way, I got 12 in parallel with 4, which if we do the math, I think is 3. So from the point of view of the battery, I saw 16 ohms. It thinks it's hooked to a 16 ohm resistor. But from the point of view of the load, it sees only 3 ohms. It thinks it's hooked to a 3 ohm resistor. So what I have over here is 3. And so I found VTH, I found RTH, And then the last thing you have to find, the value of RL for maximum power transfer. So what value, if I put RL back in the circuit, either in the original circuit or the Thevenin circuit, if I put RL back over here, what value does this need to be if I want maximum power to go from the voltage source, which I don't have over here anymore, to the load? The answer is, if I want maximum power transfer, if that's my objective, then this resistance and this resistance have to match, so I have to make this 3 ohms. And that's the Thevenin circuit. Now, you might wonder, well, what if they don't match? Well, if you, and we actually address this. When I teach AC, I go into this because this has so many applications in audio, radio, just a whole bunch of different stuff. So I actually go into if it doesn't match, there's things that you can do to get this and this thing to match. And I'll have to say more about that if you take the second part of the course, which is AC. So there's another example, and I think what I want to do, because we still got a little bit of time, I want to put one more example on the board. Now this one, the one I just did looked very similar to the one I gave you the example, the first example I started with. But this next one is pretty important because there's some new information here that I want to show you. So let me clean this up. And I'm going to put another circuit here. And according to the computer, it's 208. So what I may do is just kind of put this up on the board, get you working on it, but I might pick up with this on Wednesday, this problem. We'll end this a little early today. But let me just get you started on this. All right, so here's the circuit. Okay, so what I'm going to do is just kind of get you started thinking about this, and then I'm not going to actually work through the whole problem. We'll get you started thinking about this, because there's something new going on with this resistor I want to point out to you, and then I want you to try to work it, and then between now and I guess we do this again on Friday. We'll come back to this because this is actually very, very important. Matter of fact, this will affect not exam. I think this comes back at you on exam 2, but I think it may come at you on exam 2. I don't want to say anything that's wrong, but let me just go through this. And before you guys sign off, I want to tell you how we're going to do the lab. So if you were going to Thevenize this, what you would do is you would remove the load. You would mark the terminals. and you want to find the voltage between A and B. Here's where it's not really a problem, but here's how you got to think about this. If I connect my meter up between A and B, which resistor am I across?
3 and R2.
Okay, so somebody said R3 and R2, and that's what most people think. Because physically, it looks like that. It looks like you're across R3 and R2. But remember when we talked in, I don't know if it was lab or theory, we said a resistor, if I have a resistor just laying on the table, what's the resistance of it? It seems kind of weird, but a resistor with no current flowing through it is just a piece of wire. A resistor with no current going through it has a resistance of 0. I don't care what the color-coded value is. So basically, if you think about it, current is leaving the battery. It's going through R1, and as the current goes through R1, it'll generate a voltage drop across R1. Current's going to come down through R2 and then go back to the battery. It never goes through R3. Since no current goes through R3, if you actually hook this up in lab and you put your voltmeter right here, you would measure 0 volts, because the voltage across this would have to be I times R3, but since there's no current, this value right here is 0. And 0 times R would make this is 0 volts. So a resistor just hanging there like that with no current going through it, basically is just a piece of wire. So when you do this problem, what you got to do, only for VTH, you take this out and you replace that with a piece of wire, and then you can see connecting from A to B is exactly like connecting across R2. So I'm going to do that on the exam, and you can call it a trick if you want to. It's not a trick. On the exam, I'll give you a resistor right here like this. And as soon as you see that resistor hanging there, one end hanging there with no current going through it, you know when you're trying to find voltage, just ignore it. The voltage here and the voltage here are exactly the same. And if we were doing this in lab, I would have you build this and prove it to yourself. So with this problem, that's the takeaway. That's what I want you to see. When you have a resistor not connected, where one end is just hanging, when you're finding the voltage, just act like that resistor is a piece of wire. So what I want you to do between now and Friday is, with that information I just gave you, see if you can Thevenize this. I got this, and actually the document I'm working off of, I'm going to put this on Blackboard. If we were actually here in lecture, I would have passed this out to you. But I'll put it on Blackboard, and you can have these problems. But this is the second of 4 problems I want to go over. So between now and Friday, see if you can Thevenize it, and I'll come back Friday, and we'll pick up with this, and we'll Thevenize it. So that'll end this lecture for right now. Now let me talk about lab, what I want to do for lab. So the college is going to allow us to meet for lab this week, and then after this week, it's going to go to this is weird, but we have to do lab by remote. So I thought what we would do, and I might have mentioned this in class, I can't remember because I've been talking to so many people. Right now we have 2 2-hour sessions. And what I'm going to do is make that 4 1-hour sessions. So if you come to lab, I think your lab from 1 to 3. I think you have a lab from 1 to 3 and 3 to 5. So what I'm going to do is work up a document, and I'll put this up on Blackboard. Probably not tonight. It'll probably be tomorrow. But I'll divide you guys up. If you're in the first section that meets from 1 to 3, I'll have some of you come in from 1 to 2, and I'll have some people come in from 2 to 3. And we'll have a 1-hour lab. And then if you're in the later lab, you'll come in. I'll divide it up from 3 to 4, and then from 4 to 5. And I'll have your names up on Blackboard. You come in. What they want is just a few people in the lab so we can spread apart. They say they want us a certain distance apart. So we'll have lab this week. You'll actually come in. Now it's very, very important that you come in for lab, because one of the things I'm going to give you is I'm going to give you a tutorial on a software package called Multisim. If anybody has taken digital, you've already used a Multisim. What we're going to do in lab, we have to do lab by remote after this week. There won't be any more face-to-face meeting for the whole semester. So what I'm going to do is give you a tutorial. I'll pass it out. And I want to make it a lab that you go through the tutorial and work out to learn to use multisim. If you already do it, if you're taking digital, you're already using multisim. Or you might have used it at another institution or something. But if you haven't, it's pretty simple to use. And we're going to build our lab, and it's like a virtual breadboard. But you can get power supplies, you can get anything you need. And Dr. Whaley is working now to make sure that you guys will have access to that software via the internet. You'll be able to click on something on the website and you'll have it available on your device. If you have a PC, or hopefully it'll work on the Mac, I don't know. The point is, make sure you check Blackboard sometime tomorrow to see which lab session you come in, which time block you come in, and then I'll pass out those tutorials, and I'll give you a short lab, and then we'll call it a day. Right now, guys, I don't know how we're going to work the exams. I guess they may have to be take home. I don't know how to do it right now. Still, we're all figuring a lot of stuff out, so we'll figure it out as we go. But I'll let you know, in plenty enough time to make sure that it doesn't mess anybody up. And these sessions, I'm recording these sessions. I'll put it on YouTube or Blackboard. I mentioned that already, but I'll let you know where they are. So if you want to rewatch anything we do, you'll be able to go back and watch as many times as you want. So I have about 3 minutes. Anybody have any questions for me before we end this session? No questions? Ethan, no question?
Hello?
Yeah, so for the lab this Wednesday, what do you want us to do if there is a conflict of schedule? Because I know a few of us have an online lab that lasts until 3. So
Is that for what class?
Networking.
NetC 121.
Now, do you normally take lab on that day?
Yes.
So you'll be scheduled to come in with me. What time do you normally meet with me
3.
for lab? 3?
3 for lab.
So if you meet from 3 to 4 with me, I'll have you come in either from 3 to 4. Let me say that again. If your session is from 3 to 5, you'll either come in from 3 to 4 or from 4 to 5. So it shouldn't interfere with the other lab.
Mr.
Well, it
Singleton,
takes me about 20 minutes to get to campus, and I don't know about Julius, but so that it would cut into that time if we were to be scheduled on.
I see what you're saying. I got you. So if you need to meet from 4 to 5, then send me a text.
yeah, 18 hour. I was just saying this, Julius. I was just saying, Mr. Singleton, you can put us in the morning. I think that would be better.
If we did in the morning,
If you can put us in the morning session, me and Ete, what do you think? Morning will work with you, right?
yeah, just send me a text and let me know if you need to be. Send me a text. I think the number's on the cellars. I'll put it here. And the time blocks will be, it could be 1 to 2, 2 to 3, 3 to 4, or 4 to 5. So if you know where you need to be, just send me a text and say, hey, I need to come to that one. The thing is, we don't want like 30 people in one session because they want us to spread out. That's the reason I'm doing this. So text this number if you have an issue, a conflict, and let me know where you want me to put you. Do that by tomorrow, and then I'll put you in that block, and there shouldn't be any issues. Somebody else have any more questions?
Yeah, Mr. Singleton, actually, this is Julius. I think I tried to schedule an appointment today, but I found that the appointment was colliding with my class, one of my networking class, so I had to cancel it.
Okay. I saw you had an appointment. It's okay. That's
Yeah,
fine.
I did cancel it. I rescheduled it on Wednesday, so I don't know if it's.
That's fine. Yeah, I'll be here for my normal office hours, guys. And if you need to meet me outside the office hours, just send me a text. Don't email me. Send me a text
Okay.
and let me know if those times don't work. I can meet you up here anytime, really. With the way things are going, I'm pretty flexible. So schedule my through my normal office hours through Starfish. But if that doesn't work, then let me know and we can meet anytime. So I'll be really flexible with that, even on the weekends if we need to. Just let me know. Okay?
Yes, sir. Appreciate it.
All right, guys. I'm going to stop the recording. If you have any more questions, you can send me a text, and I will see you guys on Wednesday.